Hello. Here we'll talk about an example computation of the Galois group of a polynomial of degree 5. The polynomial will be just one polynomial examined. The polynomial I chose is t to the fifth minus t 10 times plus 2. That is a polynomial with integer and also with rational coefficients. And as such it is irreducible. Well, one way to see it is to apply the Eisenstein's criterion and choose the prime to be 2. All the coefficients are divisible by 2. The free coefficient is not divisible by 2 squared, hence it must be irreducible. And what is going to happen now is some calculus, some analysis of this polynomial, just chasing down the roots, seeing where the real roots are and how many are there. So that is standard. We start with computing the derivative, and that gives us 5t to the fourth power minus 10. And the real roots of the derivative, I should not be really repeating, because at least in this analysis part all things are real. So real roots are easy, they're plus and minus fourth root of 2. So there are two such, and just let's recall that this fourth root of 2 is in between 1 and 2. We will need rough locations for our special numbers, and it's really close to 1, way closer than to 2. So then the values of the polynomial on the roots of its derivative are, for the positive, well, we can just use that fourth power of this number is 2, so here we will have 2 and then negative 10 copies of this number, so we'll have negative 8 copies of the fourth root of 2. And that, with some little work, can be located in, it's obviously negative, and the more precise location is that it is in between negative 8 and negative 7. So similarly, the value on the negative root of the derivative is, well, similar computation using the fact that the fourth power is still 2, but then now we have the minus sign coming out, so we really have well, that's actually, yep, minus sign coming out of the single copy, so we really have the answer, which is 2 plus, wondering why is this, so okay, maybe I should do it more carefully. So I have the fourth power in the fifth power, and then the number itself, which is negative fourth root of 2, and the fourth power is just 2, so I have negative twice, and then I have negative, and then another sign coming from the number, so positive 10 times the fourth root of 2, so that is just positive 8 copies of fourth root of 2. So that is the value at the negative root. Okay, and then the limits we can put it in between integers rather, 11 and 12. So again, that can be verified with a little arithmetic computation. You squeeze this number in between, you want to squeeze this number in between 11 and 12. You can take 2 out of everything, so you will be squeezing this number in between 9 and 10. Then you divide by 8, and then you take the fourth power of the squeezing limits and the number itself and see that it's all working. Okay, so just to finish the analytic computations, let's look at the second derivative, which simply becomes 20 copies of t cubed. And there's one root, real or not, at 0, and then the value of the polynomial at 0 is of course 2. So more or less we have everything, just two more facts. Going to the far right, the polynomial will be dominated by the fifth power of the variable, and so will be positive. Going to the far left, it will be negative, but we could really see where it starts being positive and negative. So let me just compute the values at 2 and negative 2. At 2 I will have the fifth power of 2, then well, the square of 2, taking 2 out of 10 times 5, and then single copy of 2. So some again, some arithmetic will give the final answer 26, and similarly the value at negative 2, which will be 2 to the fifth, and then with minus sign, and then positive 2 squared 5 times, and then next a copy of 2. So that will be negative, but in absolute value less than 26, of course, it will be negative 18. So now I'm ready to plot a rough graph of my function. So it will be really going high with this extremal point. It will be in between 11 and 12, so I'll really have to place my graph more vertically than horizontally. So say if say 10 is some, maybe I'll extend more. So if 10 is somewhere here, and then 12 is somewhere here, so in between 11 and 12 I will have the maximum, local maximum for my function, and that will be sitting above this negative fourth root of 2, which is after in between negative 2 and negative 1, so somewhere here. That will be my point, so that is the negative fourth root of 2, and that is a number which is 2 plus 8 copies of fourth root of 2. Then yeah, you could see the signs. Obviously the sign of the derivative is positive all the way up to this root, then it is negative all the way up to the positive root, and then it becomes positive again. And so this is 2, this is where the y-intercept is going to be, and then the second extremal point, the local minimum of the function, is at the positive fourth root of 2, and the value is in between negative 7 and negative 8. So that is the number 2 plus 8, or rather minus 8 copies of fourth root of 2. So that's where the local minimum is, and then at 2 I'm very positive, and before at 1 or even at this number I'm quite negative, so I should cross my x-axis in here. I should go up very rapidly, because at 2 I'm to reach 26 height. Then in between, so this is my derivative root, and here is 1, and just between 0 and 1 I have to cross the x-axis again, because I have to reach this point, the y-intercept. So there will be a root here, there will be the root here, just very close to 0, and there will be then going up, reaching this maximum, and plunging down, and I have to shift my position for 2, -2 to a little bit to the left because I'm to cross the x-axis just before it. So that is a rough plot of the graph. And I have manifestly 3 roots, 3 real roots. x1 here in between -2 and this negative root of the first derivative, then x2 here in between 0 and 1, and then x3 here. So the conclusion of all that is that the real roots of my polynomial f are x1, x2, x3, and the rough estimates for them is x1 is in between -2 and -1, x2 is in between 0 and 1, and x3 is in between 1 and 2. And of course Newton's method can locate them way more precise as we like, but we're not really interested in it. What is important is we just have exactly 3 real roots. So if we look at all roots, and start with this real 3, x1, x2, x3, and then we should have 5. So we have x4, but then x4 conjugate should be the last one, because all the real sign here, so that must be complex, and then complex conjugate must just come for the right with x4, because the polynomial is with real coefficients. And the Galois group, that's what we're really after, that's what the title says, the Galois group of our polynomial, what can we say about it? So first, it contains the obvious symmetry which switches to complex roots and fix all others. It's called complex conjugation. So this complex conjugation, written as a permutation of roots, will be this transposition. And this is a transposition of my 5 permuted things. Another fact which I can be sure about is that since the degree of the splitting field is divisible by 5, 5 divides the order of the Galois group. And by Cauchy's theorem, there should be an element of order 5. And again, the Galois group is a subgroup of permutations of this root. And the only, well, not the only, but the only type of element for the 5 is a 5 cycle. So there should be a 5 cycle. So we have a transposition for sure. That is because of the special properties of the polynomial. And we always have a 5 cycle for any polynomial. And together we can be sure that we have to have every permutation, because any permutation is a product of a chosen transposition and a chosen 5 cycle. So these together, let me call this sigma. So it is a general fact about permutations that a transposition and a 5 cycle will generate the whole symmetric group. And hence we know what the Galois group is. Our polynomial has maximal amount of symmetries. The Galois group is the full symmetric group. We can say a bit more. We can say that the splitting field is actually the splitting algebra, because it's maximal symmetry. This splitting field has, it just must be the splitting algebra, so it is easy to construct. We can just take 5 variables, x1, x2, x3, x4, x5, and then take the polynomials in them, and then quotient by relations equating symmetric, elementary symmetric functions of those 5 with signed coefficients. So that is a splitting field. The alternative construction attaching roots is not so satisfactory because we don't really know the roots well. That's the best. Just looking at the polynomial, we can see the roots, but this is a very explicit construction. So still we have quite a good control of our splitting field. And the final conclusion is that since this group is non-solvable, the polynomial is non-solvable as well, which means that its roots are really stubborn. They should not be possible to write them as iterated radicals. That is the main achievement of Galois, really. Main achievement of the time. The solvability in radicals was considered as an important problem then. So the logic will be explained somewhere else, but the short explanation is like that. So if it is an iterated sequence of radicals, then the symmetry group of such number has to be solvable, because each time you take a root, you can turn it into an extension which has a Galois group, abelian or even cyclic, and then you really iterate the cyclic groups in an extension meta, in extension way, and so your symmetry group is an extension of cyclic groups, and it has to be solvable, and this is manifestly not, so it is not possible, it doesn't matter how much you try, to write it as iterated radicals. I'll stop here. See you later.